So here is my question. So in the undamped case, how do I get, I want to be sure that I'm getting oscillations. When do I get oscillations if, well, we get oscillations if those roots are really complex and not masquerading. Now, when are the roots going to be really complex? This has to be, the inside has to be negative. P squared minus omega squared must be negative. P squared minus omega naught squared must be less than 0, so that we're taking the square root of a negative number and we're getting real complex roots. Really complex roots. In other words, now this says, remember these numbers are all positive, P and omega naught are positive, so the condition is that P should be less than omega naught. In other words, the damping should be less than the frequency, the circular frequency. Except P is not the damping, it's half the damping or twice, it's half the damping, and it's not really the damping either, because it involved the M2. You better just call it P. Naturally, I could write the condition out in terms of C, M, and K. So your book does that, but I'm not going to. Gives it in terms, gives it in terms of C, M, and K, which somebody might want to know, but you know, we don't have to do everything here. Okay, so let's assume that this is true. Then what does the solution look like? Well, we already experimented with that last time. I'm going to first draw it. Remember, there was some guiding thing which was an exponential, and then down here we wrote the negative. So this was an exponential. In fact, it was the exponential e to the negative p t. And in between that, the curve tried to do its thing. So the solution then looks sort of like this. It oscillated, but it had to use that exponential function as its guidelines, as its amplitude, in other words. Now, this is a really, truly terrible picture. It's so terrible it's unusable. Okay, this picture never happened. Unfortunately, this is not my forte, along with a lot of other things. All right, let's try better. Here's our better picture. Okay, there's the exponential. At this point, I'm supposed to have a lecture demonstration. You know, it's supposed to go up on the thing so you can all see it, but then you wouldn't be able to copy it, so at least we're on even terms now. Okay, how does the actual curve look? Well, I'm just trying to be fair, that's all. Okay, after a while, the point is, let's try to, so just so we have something to aim at, let's say. Okay, here we're going to go. We're going to get down through there, and then this is good. This is our better curve. Okay. So I am a solution. A particular solution satisfying this initial condition. I started here, and that was my initial velocity. The slope of that thing gave me the initial velocity. Now, the interesting question is, the first, in some ways, the most interesting question, though there'll be others too, is, what is this spacing? Well, that's a period. And now, the period would be, it's half a period. I clearly ought to think of this as the whole period. So let's call that, I'm going to call this pi over, so this spacing here, from there to there, I'll call that pi divided by omega 1, because this from here to here should be, I hope, twice that, 2 pi over omega 1. Now, my question is, So this, for a solution, it's in fact is going to cross the axis regularly in that way. My question is, how does this period, so this is going to be its half period. I'll put period in quotation marks because this isn't really a periodic function because it's decreasing all the time in amplitude, but it's trying to be periodic. At least it's doing something periodically. It's crossing the axis periodically. So this is the half period. 2 pi over omega 1 would be its full period. What I want to know is, how does that half period, or how does omega 1 is called its pseudo frequency. This should really be called its pseudo period. Everything's pseudo, everything's fake here. You know, like the amoeba has its fake foot and stuff like that. Okay, so this is its pseudo period, pseudo frequency, pseudo circular frequency, but that's hopeless. I guess it should be circular pseudo frequency, or pseudo, I don't know how you say that. I don't think pseudo is a word all by itself, not even in 1803. Circular. Okay, here's my question. If the damping goes up, this is the damping term. If the damping goes up, what happens to the pseudo frequency? The frequency is how often the curve how this is high frequency and this is low frequency. Okay? So my question is, which way does the frequency go? If the damping goes up, does the frequency go up or down? Down. I mean, I'm just asking you to answer intuitively on the basis of your intuition about how this thing explains, how this thing goes. And now let's get the formula. What, in fact, is omega 1? What is omega 1? The answer is, when I solve the equation, so R is now, so in other words, if omega 1 is, if I have P, if P is no longer 0, as it was in the undamped case, what is the root now? Okay, well, the root is minus P plus or minus the square root of P squared. Now I'm going to write it this way, minus, to indicate that it's really a negative number, omega squared minus P squared. Now, I'm going to call this, because you see when I change this to sines and cosines, the square root of this number is what's going to become that new frequency. I'm going to call that minus P plus or minus the square root of minus omega 1 squared. That's going to be the new frequency. And therefore, the root is going to change so that it's the corresponding solution then is going to look how? Well, it's going to be e to the negative pt times, let's write it out first in terms of sines and cosines, times the cosine of, well, the square root of omega 1 squared is omega 1, but there's an I out front because of the negative sign in front of that. So it's going to be the cosine of omega 1t plus c2 times the sine of omega 1t. Or if you prefer to write it out in the other form, it's e to the minus pt times some amplitude, which depends on c1 and c2, times the cosine of omega 1t minus the phase lag. Now when I do that, you see omega 1 is this pseudo frequency. In other words, this number omega 1 is the same one as I've identified here. And why is that? Well, because what are two successive times? Suppose the solution crosses the x-axis for the first, the t-axis. For the first time at the point t1, what's the next time it crosses at t2? Let's jump to the 2 times it crosses. So this is I want this to be a whole period, not a half period. What's t2? Well, I say that t2 is nothing but 2 pi divided by omega 1, and you can see that because when I plug in, if it's 0, if I have a point where it's 0, so omega 1 t minus phi, when will it be 0 for the first time? Well, that will be when the cosine has to be 0, so it'll be some multiple of, it'll be, say, pi over 2. Then the next time this happens will be, if that happens at t1, then the next time it happens will be at t1 plus 2 pi divided by omega 1. That will also be pi over, that will be pi over 2 plus, how much? Plus 2 pi, which is the next time the cosine gets around and is doing its thing, becoming 0 as it goes down, not as it's coming up again. In other words, this is what you should add to the first time to get this second time that the cosine becomes 0, coming in the direction from top to the bottom. So this is in fact the frequency with which it's crossing the axis.